VSPER theory, valence shell electron pair repulsion. That's what VSPER stands for. And the basic idea is molecules will adopt a shape that will minimize repulsive forces, repulsion. Remember, electrons are negatively charged. Like charges repel each other. So the molecule will be arranged in such a way that minimizes the repulsion. For example, if you had some molecule it was an XY2 type. What I mean by that is X is the central atom and Y are bonded atoms. Okay. The examples up here do not have any lone pair of electrons. We'll talk about geometries with lone pair electrons in a future play posit. So here, one central atom and then two bonded atoms. So if you recall mathematically, so this is a linear geometry, a straight line, and a straight line the angle between these two bonded groups is 180 degrees. That is the furthest away that these two atoms can be from one another and still be connected to the central atom. So the valence shell electrons, remember those are the electrons that are involved in chemical bonding. Okay. So 2 electrons in this bond, 2 electrons in this bond. The repulsive force between them is minimized by them being 180 degrees from one another. If we look at the next example, central atom, 3 bonded groups. This geometry, trigonal planar, so trigonal for 3, tri, and then planar, because all the atoms in this molecule are in the same plane. So there would be in the plane of this screen, for example. And the bond angle between these two groups is 120 degrees. If you remember from your geometry, think of this as a circle. There are 360 degrees in a circle. The furthest that any 3 points on a circle can be from one another is 360 divided by 3, which is 120. So 120. Another 120, another 120, 120, 240, 360. So this bond angle minimizes the repulsion felt by these two bonds. So these two, the linear geometry and the trigonal planar geometry, are two-dimensional in that they are flat. The remaining groups or types are three-dimensional, and chemists use a different way of representing bonds in 3D on paper or on a screen. So the next group the XY4 type, some central atom X, so the bonds drawn here are in the plane of the screen. And then chemists to identify bonds that are not in the plane use wedges and dashes. Okay, where a wedge means that this bond is coming up at your eye. So wedges mean that that bond is coming up or out of the screen or paper. The dash is going down into the paper or the screen or in. So the wedge is coming out, the dash is coming down. So what does that look like in 3 dimensions? Okay, I'm going to switch over to the video and try and show a model of this. Okay. Click the video below and little tab, and I'll click it and compare the drawing to the video. So what's on the screen in this video is that XY4 type. Where the black sphere represents a carbon atom, but that's the central atom. And the white spheres represent the bonded atoms. So if I hold the model like so, this bond is the dash going down away from your eye. This bond is the wedge coming out at your eye. And these bonds, the way that this is being held, are all in line with each other, all in the same plane. Take and rotate it that direction. That back bond would be on a dash, front bond on a wedge. And that's a tetrahedral geometry. VSPER theory continued. The next type, the XY5 type. How is that drawn? Those 3 bonds are in the plane with each other. One bond on a dash, going back into the plane, one on a wedge coming out at you. This type of geometry is called trigonal bipyramid. Okay. Trigonal, this middle part, if you think of it like the Earth's equator, these are called equatorial positions. And then these positions are axial positions. And they have different bond angles. But the bond angle between here, 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 and here, paper it's hard to show. So again, here is 90 degrees. Like a right angle. The bond angle here is 120 degrees. Those equatorial positions. Again, if you picture this middle, 360 degrees, 120, 120, 120. And then this angle between the axial angles, the axial positions, is 90 degrees, a right angle. Now I'm going to switch over and show you a video of a model of this structure. Trigonal bipyramid geometry. So if you look at the drawing on your left, correlating that with the model, this bond is the bond on the wedge coming out at you. This is on a dash going back away from your eye. This bond, those are axial positions. That's the reason they're called axial. If you picture a planet, Earth, the Earth's axis cuts through the middle, so through the center, the North Pole, the South Pole. So the Earth is on an axis. Those are axial positions. And you can see if I turn this way, that 90-degree angle, 90 degrees, 90 degrees, 90 degrees. Okay, those are the bond between the axial and equatorial position is 90 degrees. If I rotate this way, you can see those equatorial positions in that 120-degree angle. 120, 120, 120. That is a trigonal bipyramid shape. XY6, the last basic geometry, or a geometry without lone pairs. So to draw it, two wedges coming out at your eye, and there's two dashes going back into the plane of the screen. The bond angles are all 90 degrees. So if you focus your eye on these groups, it looks like a square. Okay. And a square is 90-degree angles at each corner. 90 degrees, 90 degrees, 90 degrees, 90 degrees. Okay. These positions, as this is drawn, they're axial. Okay. Axial, the way that it's drawn. But all the bond angles are 90 degrees. I'm going to show you a model to translate this into 3D. So this is the octahedral geometry. So you can really see these bonds are the wedges coming out at you. These bonds are the dashes going away from you, away from your eye. And then these are the bonds on the lines. Okay. These are axial for the way that I'm holding it. But all the bond angles, 90 degrees, I turn and rotate it this way, 90 degrees, 90 degrees, 90 degrees, and so on. So all the angles between each pair of electrons, each bond, they're all 90 degrees in the octahedral geometry, the XY6 type.